so we're back to chapter 6, and we're looking at the what is it with chapter 6? Okay, so this is basic memory circuits, and we're going to talk through this, and we're going to try to this is one of the few chapters that does not have a lab at the end of it, but there's a lot in this chapter, and we'll talk through the chapter, and then at the end we'll talk a little bit about some problems. But basically I would like you to look through the chapter, and then next time we'll have problems at the end of this chapter, and there's quite a few, so we'll talk about them. Okay, so this is a project that you've probably seen before, digital course maybe, and you have a high and a low switch, and if you look at a circuit like this, you say, now I need to remember something, and that remembering circuit is you take an output and use it as an input. And that's how you actually can solve these problems, is using the output as an input, and that's where we're at right here. So we took the output and we used it as an input, and we remember, and what we ended up with is we tie an output back around as a remembering circuit. So this is a classic way of having a memory circuit. There's other ways, but this is one way. And this is one that you will probably have seen in some of your digital classes. And that's all this is talking through as that kind of a thing. Okay, so here is the same circuit, except now we've got a temperature switch and we've got a heater involved, but we don't really care because we're just basically going to be looking at a circuit, and I really don't care about that heater or the doesn't matter. But this does. So in general, if I want to start something, I energize it right here. And that turns on this relay, which then feeds back around it. I can lift my finger off of it, and I can walk away from it. Now the stop here is shown as a normally open, because most of the time a stop circuit is wired in the field as a normally closed. So if you show it in the field as a normally closed, but as a normally open here, you have the normally closed function. Hopefully you see that. Hopefully you'll understand that by the time you get done. So we now get down to relay type of instructions. And what kind of instructions are those? These are the ones that we've been using: normally open, normally closed. This is one that Siemens uses that Allen Bradley does not use, which is the not function, which basically takes the inverse of something. This is the coil. This is the not coil. This is a reset and a set, which is like a memory circuit. This is the set and reset block. This is the reset set block, and this is the positive transition, the negative transition, and this would be a positive transition leading edge or positive leading edge as a coil. Allen Bradley does the same basic things. They don't do quite as much of it, but they do basically the same thing. So this would be the same instruction set as the Siemens instruction set, but with a little bit fewer of those specialty items. But you can do the same basic function with either one. So I'm going to let you look at this part of it. I'm not going to go through this in detail. I'm just going to let you look through it, and we're going to skip down here to a part of this that's pretty interesting. Okay, so I'm going to let you read through this on your own, and I'm going to look at it, and I'm going to say, okay, now one of the things that you do probably not remember, but from chapter 1, we talked about IEC 11 or the 16131-3, whatever the common language was. Well, there is this common language where you use the set and the reset as two coils. You can also use it as a block, and my recommendation is you do it as this block because it makes a lot more sense. Everything is compact and it's right there in front of you. You can do it either way, but this works, that works, but either way it's the same. So we're gonna go down through here, and now we're going to talk just a little bit about a latch coil. A latch coil is different than a relay coil in the sense that if you lose power, it stays in its last state. This is a physical switch that resides in either the one side or the other, and it has two coils usually. There's two coils, or there's one coil and some diode arrangement, but basically there's two coils. You can see the two coils here. One is called the reset and one is called the set. So that is making that bit retentive, and most of the time that is not what you want. You do not want to have a retentive circuit. You want to have one that if you turn the power off, it drops out. Now this is the old, what we would talk about as a control circuit, seal circuit. So this would be a relay that you would actually wire up, CR and the CR and the start and the stop, and we did this in chapter 2. Now this would be a latch coil that you do the same thing with, and you must put both these in, or else you have the possibility of burning up one of these coils. If you have a physical latch unlatch relay, the coils can actually burn up, and you don't want that, and that's only for physical latch relay coils. Okay, so now we want to talk about, I have a start circuit and a stop circuit, and I wire these to a PLC. Okay, now this is a start with memory, and then the stop button. Okay, so the stop is often normally closed, so you push the button, it opens this. Do you see that? If you push the button, this turns off, and this was on, but now all of a sudden it goes away. So normally closed here, normally open here gives you a normally closed function. You push it, and it turns off. The stop on the start, on the other hand, is with a this is with a normally open button. So normally open button and normally open here gives me a normally open function. Now what is this? Well, it's the same memory circuit, except there's one big difference, and that is with this circuit right here, if I push the stop button, it turns off. If I push the stop button here, it turns off if nobody's holding their finger on the start button. However, if somebody is holding their finger on the start button, this guy does not turn off. And this is a very dangerous circuit. You would never program this circuit for anything that runs. You would this for something that runs. So where do you program this? What do you program this to? Well, let's say something that's bad. Let's say there's an alarm. Okay, so the alarm turned off, or the alarm turned on, and we hear a horn, and we go out to check it, and what do? Well, the first thing you do is you push a reset button. Now the reset button is this guy right here. This would be a stop, it'd be a reset. It's turn that horn off, stop the horn. So if this turns off, the alarm has turned off. It may come back on eventually, but for right now it's off. If it's still on, if the alarm is still on, it passes power, and you see it is still passing power. In other words, you'd put this to a light. So this way says, I saw it and I captured the fact that it turned on. It's a bad thing, it's an alarm. I do not care, I'm going to turn it back off. So that gives you the idea of an off dominant or an on dominant seal circuit. Which is better? Well, it depends on what your application is, doesn't it? If I'm turning something on that I want to make run, I use this circuit. Never use this circuit for that. However, if there's something bad, like an alarm, that I want to check, I use this circuit. So that gives you a basic format for using a memory circuit, and these are memory circuits basically the way they've been designed in the United States. I'll tell you that most of the people that write programs in the United States write memory circuits based on this concept, right here and right here. Most of the time it's this for making something run, but for an alarm circuit, this is what they do. Okay, so how do you change from one to the other? You never would do this, but how would you do it if you did do it? You'd move the stop button down here, but leave it in the same basic position, correct? That's exactly what you do. Okay, so now we have a Siemens circuit. Remember, we have the start sets the bit, the stop resets the bit. So set is above reset. This would turn it on, this would turn it off. Off dominates because this guy wins, second guy wins. So if you're pushing the button, you're resetting the circuit. If you are not pushing the stop button and you hit the start button, it turns on. You lift your finger off the start button, it stays on until you hit the stop button. So that would be an off dominant. In other words, the off or the stop would dominate. How would you do the opposite? How would you do an on dominant? You'd flip the reset and the set. Set is on the bottom, reset is on the top. Now this is an alarm circuit. This would be something that you would do an alarm with. And it's the same way as Allen Bradley does the latch. They have a latch circuit which mirrors or is the same as the reset and the set. This would be the set, this would be the reset. And the off dominant circuits. You say, do I have to memorize all these? I don't think so, but I think you ought to learn them. You ought to learn how these work. I think it's important that you learn how these work and practice with them a lot. So as you're writing circuits, you will probably go back and refer to these from time to time. And I hate to tell you this, but most times it's not just one contact, it's many contacts. So as simple as those circuits were, it'll be a bunch of contacts that usually are the case. Now, how does Siemens work their retentive memory versus non-retentive memory? Well, when you open up a 1214 or a 1215 processor, they have a line in the M table, and that line in the M table is set to 0. You can adjust that line. Anything below that line is retentive. In other words, it would act like a retentive circuit. If it was above that line, it would be non-retentive. So basically, an R and an S in Siemens, if you turn the power off, it comes back and it's in the off position. But if it's in that area that is below the retentive line, it would come back in its prior state. So they use the retentive nature of this table, and a line in that table determines whether or not those words or those bits are retentive or not. So again, they do it one way, Allen Bradley does it another. The Allen Bradley approach is to, if you have retentive, you define it with an L and a U, a latch and an unlatched bit. So that's how they do it. They both do the same thing, but they do it differently. So what is this? Well, it looks like a bunch of gibberish to me. No. Now you look at it and you say, this bit right down here is the same as this bit. So this is a feedback right here. So what is all this? It took this combination to start this. So somewhere in the line you had something, this is one way, this is the other, but it's either this or this will turn this on. Then you can lift your finger off of this. These could go back to an old state, but it continues to run until what? Both of these turn off. In other words, this one or this one, it's not this one or this one, it's this one and this one are in the off state. Either E is off or F is, either E is on or F is off. We'll stop this. Okay, so that's how that's done. Now, how would you take this and make it a latch? You would take this portion right here and run it to the L, and you would do what with the unlatch? You would take the De Morgan of this portion. Look how that happens. You take the De Morgan and make it the unlatch. Okay, that's how that's done. Now, why would anybody use retentive memory? Well, good question. It's not recommended because most machines are designed so that if you turn the power off and turn the power back on, they revert to a known or simple state. That is important. You need to remember that they have to revert back to a known or simple state. If not, if you use latches in your program, a lot of latches in your program, you will find that your program will be known as the machine that had a mind of its own. So if you hear somebody that says that machine has a mind of its own, typically those programmers or program people that program that use latch relays, a lot of them. So if you want to be safe, do not use latches or do not use retentive memory and Siemens, but do use the seal circuit or the non-retentive set reset. So that would be the safe way of doing it. I had a guy who was the head of the body shop at Jeep, took the course a long time ago, but he took the course, and he said he never lets the programmers, the electricians that program for him, use latch coils. He said they only can use seal coils from Allen Bradley. The reason for that is very simple. It's he wants to be able to go up to the machine, turn the power off, turn the power back on, recycle power, and reset the machine to a known starting state. He doesn't want it. He doesn't want to have to battle with something that resets itself in the middle of some sequence. So it's another way of saying I want to save myself from having a lot of 3 a.m. calls. It helps. So don't use latch relays unless you absolutely have to, is the bottom line in most circumstances. There are instances where you need to, but they're very rare. Okay. So just to remind you that you can do the same thing with function block diagram as you can with ladder. And here's an example of function block diagram. Yes, you can program in function blocks as well as ladder. So this is a review of that portion. Here's the Allen Bradley, here's the Siemens equivalent. Here's the Allen Bradley, here's the Siemens equivalent. For retentive circuits, here's the Allen Bradley, here's the Siemens equivalent. Okay, so that gives you a little bit of an idea. So now that we've learned what they are, how do you use them? Well, originally I did not ask, when I was teaching this course, a lot of logic, but I just taught the basic symbols. Now I ask for logic. Anytime you see a vessel like this with a high and a low switch, it's begging you to use a seal circuit or a memory circuit. Well, how is that? Well, here you're getting water or liquid from above, and when it goes to the high level, you want to pump it out. You say, where does this exist? Where do these exist? And I want to remind you that they're all over. And one of the examples is anytime you flush your toilet in your house, where does that go? Well, it goes to a holding tank somewhere, and I don't know where that is, but it goes there, and it goes there until you get to the high level. When it goes to the high level, the pump turns on, and it pumps that liquid to Bayview, the wastewater treatment plant, and there the water is separated from the bad stuff, and the water's put out in the lake, and the other stuff is I don't know what you do with it, but anyway, it goes away. So that is, every holding tank has one of these systems. So what happens is when it goes to the upper level, you pump until it goes to the lower level. Now you say, well, does that need a memory circuit? Yes, because once it goes above the upper limit, then it starts to pump and it goes below the upper limit, and you do not want it to turn off there. You want to remember that, hey, I was above the upper limit and I stay on until I go below the lower limit, and then I turn off. So in this whole middle range, it's a memory circuit because you have to remember that I turned it on and I don't want to turn it off until this guy hits it, okay? So in other words, I don't want to have to put a person out there to watch that happen. I want an automatic circuit to do that, and this is how that's done. Remember, all the way down to here. So that's a memory circuit. You need to remember. That's what that's about. So again, we'll see a lot of these, but that's exactly how that works. There's your switches, and your start switch, your stop switch, and there you go. This is the exact opposite. This one, the project or the process is taking liquid out. We don't know how, we don't know exactly the rate. It doesn't really matter. But when it gets to a low level, we want to pump in more and bring it to an upper level. Well, what starts this? The lower level starts it, doesn't it? What stops it? The upper level stops it. So basically, this is just the opposite of the other one. What if I have something that's really critical? I want to put in a start switch, and then I want to put in another start switch that's just a little bit below that one. I call it the low switch. So if this one doesn't get it, then this one will. And about the high, I have a high, and I have a high that turns it off. If this one doesn't get it, this one does. And what else do you want to do if you get to this one? You want to sound an alarm, don't you? Because you want to tell the operator that they need to get somebody out there to fix this switch. So you see that this has double duty. This one it saves your logic, it saves your process if this one doesn't work, and also gives you an early warning that you need to fix this switch. So both of those things are going on. Okay, so the use of alarms, we talked about that already. That's in this section. Now we want to talk about one-shots. And this is an important topic as well, because positive and negative transition circuits are everywhere in logic, and you definitely want to use them. You want to know how to use them, but you also want to make sure that you can use them. So the original picture of a one-shot was either this one or this one right here. That's a leading edge one-shot. And this is a negative edge one-shot. In other words, it went around my program one time if it saw a leading edge of a signal. That signal could stay on for a day, it could stay on for a minute, it could stay on for a second. But at the leading edge of that signal, this is going to go through my program one time. It's only going to go through it one time, but it is going to go at that one time, and that's it. So that's how it started. And they also had a Modicon, that's the program controller that used these first. They had logic that saved all the inputs, and they called it a last scan table. You didn't have access to it, but it was there. It was the last scan. And there was this idea that really did make it easier. Well, it made it easier for them because they had a real simple data table. But as we got more sophisticated in our data tables, that idea of everything being collected every scan became a little bit prohibitive. So with everybody else besides Modicon, there are two bits. There is the bit that we look at for the leading edge, and there is this other bit that we probably consider a wasted bit. For most of the applications, this would be a wasted bit. But what is it? Well, it is that last scan bit. So in other words, this is going to pass power when this turns on, but this was not on. In other words, this reports what this bit was the last scan. If it was on, but it was off last scan, let it pass power. Then this sets, and then you don't pass power again. So the bit on the bottom is a wasted bit, but it must be unique. You must waste a bit in order to get a bit. So in other words, it's a wasted bit of sorts. You can use it for other things, but it has to be unique. It has to be there, and you have to basically sacrifice that in order to get a one-shot. Not a big deal, but you have to do that. Okay. So that's for Siemens. Now, how does Allen Bradley do that one shot? Okay. Now, I want to say this. This is the way typically that you would use one shots. You would use them to set a circuit, but not to reset a circuit. In other words, you can turn a circuit on, a memory circuit, but not to turn a circuit off. And this is something that you want to consider when you're using logic. If the logic isn't working, you perhaps want to change it to the one shot in the start circuit, not in the stop circuit, but in the stop circuit, in the start circuit, in the start part. Okay, so here is the one that you want to use from Allen Bradley right here. So you push this button. This is a blocking bit after this has been on for one scan. So in other words, this branch right here is the start part of the circuit. So this is a seal circuit. Third is a seal. Start is the start part of the circuit. Stop stops the circuit. But if this signal, if you don't get this thing to work with this signal right here, drop this in and see if it works, because it very well may. You may want to seal a circuit based on the start, the leading edge of the start part of a circuit. And believe me, this is very powerful, and a lot of people use this concept for starting a seal circuit right here. Okay, so how would you do that one shot? Well, some one shots just naturally occur in circuits. The hot dog internal bit was a one shot. It was only on for one scan, reset itself, and went back off. It was only on for one scan. There's no reason to use a OSR bit or any kind of a bit on it. Just realize that it was there. Okay, so what is this? Well, this is a circuit that takes a push button and makes it into a toggle switch. So I built my panel and I wanted a toggle switch, and I put a toggle switch in my report that I wanted to put it in there. But the guy that did the design missed that, and he put in a selector switch. He put in a, not a selector switch, but he put in a push button instead. I need a toggle switch. No, we don't have a toggle switch. We only have push buttons. Okay, how do I do that? How do I make that into a toggle switch? Well, one way is in software. And this may not look like a very interesting circuit, but it is, because this is a push button that then sets on a one shot. Okay, the one shot then says, was it previously on? This usually is off. And this would be the reset bit right here. So basically, push the button, the one shot sets this bit, which turns off this circuit if it previously had been set. So every other time you push the button, this turns on. Every other time you push the button, this turns off. If you don't believe it, put it together and try it and see if it works. It works, and it works very, 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 very well. It's exactly how this circuit works right here. The button, the one shot, and every other time you push the button. See, you basically have built a frequency divider. And here is another example. These are three events that are occurring, and they never overlap. These are three events that are occurring, and they do overlap. Okay? Now, if I use this circuit for this, it will not work. So for this kind of circuit to work, I must remember which one turned on last. Hopefully you see that. So a lot of logic has to be executed on leading edges. So again, this is another example of use of one shots. Typically, one shots are used to start memory circuits. Stops, hard stops, are used to stop memory circuits. It's exactly where they're used. And we're going to look at this just for a second, in that you had a memory circuit that said, I am in the fill phase, I am in the condensing phase, I'm in the draining phase. So in other words, you need to remember what you were doing. In other words, you set up the selector switch, not the selector switch, but the memory of which one you're actually doing. I'm in the fill, I'm in the condensing, I am in the draining. You have to remember which one you're in. Okay, so here are some circuits, and we're going to not go through these right now. We're going to work on these as problems at the end of the chapter, and we do save some of these to actually work on. So I'm going to work on these as problems at the end of the chapter and let you look at these, and we'll talk through them as we work on them. Hopefully by that time you'll have the questions answered as to how to make some of these things work. Okay, so this is chapter 6. Hopefully you get a chance to review it, and hopefully get a chance to look at the problems at the end of chapter 5. And we'll talk through in our next lecture, we'll talk through the problems at the end of chapter 6, and then we'll probably then move on to chapter 7. So this gives you an idea of how we're going to go through some of these chapters, and hopefully you're staying up with us in your reviews. Hello, I want to go through the problems at the end of chapter 6 with you, and also wanted to go back and review a problem at the end of chapter 5 that if you were thinking about how to do the coin problem with a bunch of push buttons, and you for some unknown reason you basically wanted to hold those buttons down. In other words, I've got a push button here, and I want to take that to an input, and that says quarter one, okay? And I want another one that says dime one, okay? This would be quarter one and dime one, and then I want to do a request. Well, I could do all three of these holding my fingers on those and then hitting the request. That's doable. Or I could put a jumper over. That's doable as well. But let's say that I'm lazy and I don't want to do that. Well, then that moves us into a memory circuit for this. We want to remember that we pushed quarter one, that we want to remember that we pushed dime one, and then we do this last. Okay? So how do you do that? Well, one way is to have something that we're going to turn it off with and then design a seal circuit. And you can tell I'm a seal circuit type of person. So this would be quarter one, and quarter one remembered, and you seal it with right here, quarter one remembered. Okay? And dime one, you'd have dime one, and you have something over here that turns it off. And I got to do the path right. I got to go through and do the path part of it right. But you have these circuits, dime one, and you'd have dime two, and you'd have all of these. You'd have one for each of these, right? And then you would have dime one remembered, and you would have quarter two remembered, dime one, dime two, dime three. All of these would have a seal circuit. Okay, so this is kind of a mixing of, this is chapter 6 stuff. This is chapter 5 stuff. So now we're saying we could have made that chapter 5 problem easier if we had a little bit of chapter 6. And that's true. But now what do we do for this? You think about what you would do to turn that circuit off. Well, you say I have an extra button. I add an extra button. I could add a reset button, and there's nothing wrong with that. That's perfectly legal. Have a button called reset, and we're done, right? Not of reset, boom, splat, done. Or make this a normally close. When we push it, it resets. So there's nothing wrong with that. There's nothing wrong with that, except for the fact that I have to add an extra button. I'm lazy. I don't like to do that. So how would I do that without adding an extra button? Well, the key is in chapter 6 if you want to, and also in chapter 7 if you want to. There's two answers, and they both are equally good, and they both work, and either one of them, I don't care. But you can do whichever way you want, or you can do it another way. It works. The answer is, what's the right way? My answer to you would be, does it work? So that's the way this course is run. Does it work? Go for it. So that's basically what I'm going to ask you to always do. So when I push the request button inside the program, I have the normally open of the request button, and I have the normally closed. Okay? When does this happen, and when does this happen? This happens when I push the button. This happens when I don't push the button, or when I just let go. So basically, I can take this right here and say what? I can use that, can't I? So I can say this And if I was an Allen Bradley man, I would then put an OSR here. Or it's the blocking bit. It's the blocking bit for it, which is I forget the exact nomenclature, but that's what you do. You do the blocking bit, and you go to an output. Or if I am a Siemens person, I do this. I do the negative edge of the request going to, and this is down here as a request with a junk bit. Let's call it a junk bit. Going to a bit called A, and on the negative edge, I turn on A. A comes up here and turns this puppy off. It works. It's a negative edge one-shot, and that works. That's one way of doing it. What's another way of doing it? Well, I don't like one-shots. I don't understand them. They're new, and I'm not comfortable with one-shots yet. What would be another way of doing it? Well, you peek into Chapter 7, okay? You peek into Chapter 7, and at the end of Chapter 7, what do you see? Timers. So when this turns off, I go to a timer. Go to a TON timer at a half a second, and then with an output, okay, which would be, with Allen Bradley, it's the .done bit. With Siemens, it's the .q bit. So let's just go with the .q bit, okay? This is the .en bit, or excuse me, the .in bit with Siemens. So the .en bit, okay? So if you say the .en, so this would be timer .en or .in. But not .q, you get the same bit, A, which is on for half a second. And that bit then turns off that up there. So when you let your finger off the button for half a second, A turns on, which turns that off. Either way works. So do you see how Chapter 6 all of a sudden gets, Chapter 5 gets swallowed up with Chapter 6? Because almost everything somewhere along the line needs some memory circuits. And that's the point that I'm making there. Okay, moving along. Chapter 6 questions. Number 2. Okay, so this question is a filling of a tank. Okay, so here it's being filled automatically from above. So we have a tank, we've got a pump that's filling, okay? Going out, we don't have control of. So this is not on our control. We do control this pump. So we have an upper level, we have a lower level, upper level, lower level. So we have a switch at each one. Now, what do we call this level high, level low. So what do we know? What turns this on? We start pumping when it turns from below, right? So we draw our seal circuit, and we leave everything normally open for the time being. So this is my pump. What turns it on? Low level does, doesn't it? Okay. Now the low level, when it goes below the switch, you want it to turn on. So if the switch is built like this, it's a normally open switch, right? When it closes, it is that's a normally open switch. When it closes, it's off. When it opens, it's on. So that would be a normally open switch. Do we want a normally open switch, or are we doing a normally closed switch, which would be this one right here? So normally open switch opens, normally close switch closes. Now this one would be the one that would be like pushing a button that when it goes low, it turns on. So that would be this way it is right here. This would be the other way. Now you have to ask the question, what happens if a wire falls off? Here we do not, if a wire falls off, it would start the pump. We do not necessarily want that. Do we want the pump always on? If the pump is always on, it's going to overflow, isn't it? It's going to be like, well, not necessarily, because the high switch is going to turn it off. So we have to ask the question, which would be better, this one or this one? I probably would pick this one because it's normally open, and it would only turn on when it went low. So in other words, if we fell off a wire, this would never turn on. So I'm going to keep this one. This would be our normally open, okay? Now let's go up here and ask what happens when we go to the high level. If the high level switch, and we have to picture these switches kind of as like this, that would be a normally open, or normally closed like this. So when it goes off the high level, in other words, when it turns off, does this turn off or not? So here, I'm going to pick the normally open as well, because if a wire falls off, the pump stops, which is kind of, you want the process to stop. And this would be this right here. This would be a high level, level high, and level low. So now we can draw our table. So our sensor, level high, is an upper level switch, and it has an assignment of a 1, and a lower level has a lower switch, and it also has an assignment of 1, and our pump has an assignment of 1 as well. So that would be a good answer for that one. Okay, moving on. Number 3. Okay, now this is something that we talked about you would never do, but just to show that you know what an on-dominant versus an off-dominant switch is, here is a question. So I have, this is my question, I have A and B naught, and then I have my seal around this. Okay, so this is my start of my circuit. Does everybody see that? It takes these two to start. Okay, C and D are my stops. And you can say, do I have to put them in front or can I put them in back? I could put the C over here and the D over here, or I could put the C and the D over here. It doesn't really matter. They stop this puppy, and then I go to my E or my seal circuit. Okay, so how would I change that to an on-dominant? This is an off-dominant circuit. These dominate. How would I do it the other way? Well, in an on-dominant circuit, this would be not a good thing you would ever do, but just to answer the question, A and B and then E down here, and an on-dominant circuit would move these two down here, C and D, and now I can have an on-dominant circuit that the on, if you press it, never turns off. Now, what would this be used for? This would be actually for motors and stuff like that, right? This would be used for alarms. Not the same entity. These are never the same. Never the same, but that's how you would do that question, okay? It's number 3. Number 4. Convert the following to a latch, then to a set reset. So how would you do that? So now you have to spot again where the seal circuit is. You're always looking for where that coil is. It's your back feed or your feedback circuit from, and here it is. Here's my E. So this is my feedback. This is the start portion. Now everything over here, and I can draw it like this, or I can draw it the way it's in the book, or I can draw it like this. Makes it a little bit easier to see if you do it like this. And this whole thing has to, either path here can stop it. So basically, if you lose both, lose this path and this path, or if you just lose one, the other way will carry it. So this is kind of an odd stop circuit, but you can have stop circuits like this. Not that you would design a lot of stop circuits like this, but you could. So now this is where we start. How do you convert this? So to a latch or to a set reset, you would do the following: A, not B, to the latch of E, and the De Morgan of that circuit up there. So it was a C and C naught and D, so it would be C or D naught. Okay, so you take the opposite. D naught. So that would be the opposite of that, and it was ORed with the F, so now it is ANDed with the F naught. Goes to my unlatch of E. So the same bit is in both places. E is for both. Just instead of one, it's on both. Now how do you do it for a set reset? Well, you just change the L to an S and the U to an R, and you got it. So the A and not B go to the set. So this would be Allen Bradley, and this would be Siemens for this bit. This would be the C and not D, and the not of F, and this would be the reset of E. So if you were in the United States and you were solving this, you would probably see this. If you were in Europe, and if you were in the United States and you wanted to make it a retentive memory, you would do it like this. If you were in Europe, you design it like this. So this would be the German or Europe approach. Can't spell Europe with a U. You say Europe. E-U-R-O-P-E, Ted. This is the European approach. Typically, the way they design circuits, you may design circuits this way because this is traditionally how they've done it. This is the way that the United States done it, although there's no benefit one way or the other. It's just that they answer the question. Okay. So I'm going to let you do number 5, number 6. Okay, and number 8, I'm going to let you do up through 10. Now, number 10 is there for a reason, and this is from a book. Number 10 is from a book from Germany. And some of the stuff, as you can actually see, is still in German. But I want you to just look at how they do their circuitry. It's not that we're going to ever ask you to do it exactly that way, but that's exactly what you can. Now, number 11. This is FBD, function block diagram. We don't do a lot of FBD in this course, but I do want you to understand the function block diagram can be used. And how do you do it? How do you build it in ladder? Well, you would look at it and say, oh, okay, what are those little boxes with ampersand in there? That's an AND block. How do you build an AND? Well, for input 1 and input 2, you would say input 1 and input 2, period. And then that goes to something we'll call an intermediate bit. Let's call it A. And then later on, we're going to talk about the not of A, because that's going to be what's going to feed our OR circuit. Okay, so the not of A is going to feed our OR circuit. We see that it's an AND circuit. What about this block right here, the greater than or equal? That is an OR circuit. Okay, so we have ANDs and we have ORs, and we also have set reset. So basically, we have input 3 and input 4. Everybody see that? Going to the set of a bit. Let's call that B. You have to come up with a name. And that other one, greater than or equal, is a OR. So 5 or input 6 go to the reset. Now you can either draw a set and reset, or you can draw it with a block, have S and R in it, and you can do it like that. Either way works. Call this B, but it's the same thing. Either way works. Okay, this and this are equivalent. So now that I have A and that I have B, and I notice that I have an OR circuit up here, this last thing, greater than or equal to 1, so it's basically, it is the not of A or B knotted or input 7. Give me my, let's call it my output 1. So that gives you an answer for the FBD to ladder conversion, and I want you to be able to do that, okay? 12, and anyone that you see this has a star on it has been asked on a test before, so 11 and 12 are the same. I'm going to let you do those as you see fit. 13. So number 13, okay. Now, this is kind of an interesting question because it's a thinking question, and it's obviously a test question. People have asked it before. But what are my inputs? S. What are my outputs? H1 and H2. So every time that S1 turns on, something happens, doesn't it? So S1 turns on the leading edge, doesn't it? So it doesn't depend on how long it's on, it just depends on the leading edge. So the activity is on the leading edge. So let's try doing this. So let's just say S, positive edge of S. And this is S junk. There's a bit that has to be used, but it's just a throwaway bit. So let's do that. Let's call that, let's take that to a counter, okay? CTU. And you say, we haven't talked about counters yet. Well, no, but you can kind of get the idea. This is a counter, it counts up. And once we count to 3, it turns off, doesn't it? So we put a preset at 3, okay? And then if we say that this counter, let's call it counter 1. If counter 1 is greater than 0, then I'm going to have on H1. If it's greater than 2, greater than or equal to, if it's greater than or equal to 1, greater than or equal to 0, greater than 0, Ted. And the other one is count 1 greater than 1, turns on H2. When it gets to 3, what does it do? Turns off, doesn't it? So when it gets to 3, go to the reset of that counter. Okay, so this may be a problem that maybe we should move to another chapter, but again, this is one way of doing this. Another way of doing it would be to set memory bits, which does the same thing, but I like the counter approach. Anytime you can count something, don't set memory bits. It works better if you do a count. So again, this is one of those things where many ways of doing it. Okay, number 14. This is one we've already solved. I'm going to go to the next one. Number 15, we've already solved that one. So we're going to go to 16. Okay, so number 16 is a little different. Up until now, if we have a coil over here, it's usually an output. That's not always the way it is, and many times it's not the way it is. So basically here, we say, I read the problem, a box is placed on the conveyor, C1, then the operator pulls the pull cord, and the conveyor starts. If C2, the second conveyor, is also running. If not, the conveyor waits until C2 starts and then turns on. In other words, we do not control C2. Something else does. We don't even know what's going on over there, but we know that unless it's running, we're not going to run. The box moves until C1, on C1 until the trailing edge passes the photo eye, and then it stops. Okay, and waits for another box. So here, we do a seal circuit because most things now require some kind of a seal circuit. And we do the pull cord. The pull cord or start button, PB1, starts something, okay? And it says, does it say run? No, it says try to run. Try to run C1. And you seal it. Okay? I don't know what's going to stop it yet, but I don't really care right now. So I just basically say, I got a box on there and I want to run. So try to run C1 and C2. That does what? That runs C1. This is my output. Question, is the output the output of the seal circuit? No. In this case, not. And most of the time, it's not. So many times, this is the way it is. You do a seal circuit, memory circuit that does something, and then you see that. Okay, now, how do I turn it off after it goes past photo I2? Okay, photo I2, negative edge, excuse me, photo I1. The negative trailing edge of photo I1 sets up a bit, call it B, and when B turns on, that turns off. So when the photo I turns on and then turns off, at this point I want to turn off, this is my photo I. When this happens right here, I want to turn off this circuit and let it rest. Okay? Does that make sense? That's how it works. What's the deal? No more do we have to tie by any kind of a rule an output to a coil, or output to use the internal coils to set it up, and then that's it. Okay. Now number 17 is the same thing, only it's a little different. Here, we always ask the question, what is it we're trying to do? We're trying to fill either bin 1 or bin 2. So we've got these two bins at the bottom, bin 1 and bin 2. Now I'm going to say this, and it may or may not gel, and it may or may not be the exact thing how you work, but many times you work problems from the bottom up. So you concentrate on the thing at the bottom, and then you work your way backwards, and that's how a lot of logic is solved. So what do we need to know? We need to know if the bin is being filled. If it needs to be filled, it should be filled. So how would you do this? With a seal circuit, right? Or a memory circuit. Let's just call it a memory. Again, I always go to this because that's the way I was taught. You may say, I like set resets better, or I like latches better. If you say I like latches better, I'm going to say you better think about it, because these are the circuits that got a memory of their own. But I don't really care whether you use set reset or seals. Your choice. And you say, well, I'm working on Siemens, but can I use seal circuits in Siemens even though it's the German? Yes. They give you the opportunity to, yes. It's just if you are working on a circuit that's written by an American, typically they use seal circuits because that's the way they were taught. Typically the Germans use set resets because that's the way they were taught. That said, you can find a German who likes seal circuits, and you can find an American who likes set reset. It's up to you. They both work. So how do you do this? Well, I do the same thing I did before. Set up a circuit like this, right? Kinda, right? Because now you have to worry about competing resources, okay? Something turns it off, but here's my bin 1 fill, okay? Here's my bin 2 fill. And here we actually do use this seal circuit as our output. So we actually, no, we don't use it as an output, but okay, so I'm sorry there. This is bin 2 fill. So this would be my low for bin 1, and my not of my high for bin 1 and not of my high for bin 2. So basically that's easy, but I cannot be serving them both at the same time. I would become something. So you can't be doing bin 2 fill if you're doing bin 1. I can't be doing bin 1 if I'm doing bin 2. Does that make sense? So you don't let it seal unless the other one's not busy. And for 2, that works pretty well. When you get more than 2, it doesn't work as well. But here's your seal circuit, and that starts everything from there. So from there, then you go over and you say, well, what else do I have to do? Well, I have to run the conveyor. I have to run the conveyor to the left. So if I'm doing bin 1 fill, do you see how that drives the conveyor to the left? C2 left. If I'm filling bin 2, you see where I'm doing C2 to the right. So everything follows after this. And the screw conveyor, and again, screw conveyors are very dangerous things, but be careful. If you ever tie yourself up with a screw conveyor, be aware of the fact that they are very dangerous and they can cause a lot of damage to you as an individual. Be very careful around them. So conveyor 2 left, conveyor 2 right, either one turns on that screw conveyor. Now the low and the high on the bin 1, storage bin, is another issue, and that's just like you would do with a with your liquid fills, the same thing, and that's your conveyor filling. It'd be like a pump, same thing. So that gives you your answer for the majority of number 17, and that's a good place to stop with that one. Number 18 is a batching application. Batching. And if you don't use it as a batching application, it becomes a sequencer. So you do the first thing, then you do the second thing, then you do the third thing, and then you're done. Okay, so we're going to talk about this in chapter 13. We're going to talk about this in chapter 11. So we're going to kind of hold off on this one a little bit, but if you want to try it, you can. It's not a bad problem, but it's not one that we ask on tests typically, and it's one that I want you to understand that there's more to this than just chapter 6. But again, we'll work on it. Number 19. This one is, if you start at the end, at the right, and then you work your way back, everything follows from the very first. So the very first thing is high level, low level, right? Just like with the pump, this is bin 1, seal, low, high, okay? So it's demanding. I'm saying, give me something. So you run conveyor 3. If bin 1 says I'm on, you run conveyor 3, right? You hope to run conveyor 3. If conveyor 3 is running and you don't have a high level, you're going to run conveyor 2. And I think what you want to do is use a normally open switch on that level switch there. So again, you have to ask the question, if a wire falls off, would it be better to turn it on or turn it off? And I think you want to use it that way. And then what do you do for, that would be level 4, and then how would you run conveyor 1? Well, if conveyor 2 is running and level 3 is not high, then you run conveyor 1. So this one works exactly in reverse order. To the right, move to the left, move to the left, move to the left, done. Okay, we're not going to do number 20 right now because it is very similar to, we'll just keep waiting on that and pushing it back. But number 20, number 21, I'm going to talk about for a minute. You say, there was a guy that wrote an article, and he wrote a whole article about it, and you can Google it and find it. His name is Dave Perkon, and he's a technical editor for Control Design, and he wrote a test for an interview for a controls job. And during the interview, I simply ask in writing that the applicant draw a start-stop circuit ladder diagram using the following hardware: a normally open push button, a normally closed push button, pilot light, and a double pull, double throw relay. I also noted the requirement was to turn on the green pilot light when the momentary start button was pressed, and to turn off the light when the momentary start button was pressed. Okay. Also ask the applicant to wire the number to put wire numbers, device designators, and relay cross-referencing. So I'm not going to solve this for you, but I will say this. You should be able to pretty much design this and realize that this is an old guy with expectations that you have some ability to do the old relay stuff, the chapter 2 stuff, in addition to the PLC stuff. So as you're getting going and you're asking yourself, now, how am I going to get a job with this? How am I going to make money at this? By the way, in his article, he says that very few people that cross his paths can solve this problem. It's an easy question. Just be careful that you do not go so fast into the PLC side that you forget that there are people asking this kind of question as well. So I'm not going to make a big deal about it, but I do want you to understand that it's okay. So number 22. This is a review, a different view of how to do the car wash. So if a bay turns on, one pump automatically turns on. Okay, so if I turn either bay 1 on or bay 2 on, so that bay in use or that bay 2 in use, either one will turn on pump 1. Okay, now if there is not enough pressure, P1, and not enough pressure, so I have a timer. Not enough pressure. Okay. So I let it go for a while, and if not, what happens? This turns on pump number 2. And you seal this circuit. Okay, let's call this A. The output would be A. So pump 2 runs until something happens. Okay, so let's just say as long as, if you read through there, as long as you have pump 1 on, pump 2 is going to run. If pump 2 turns off, pump 1 will turn off. If pump 1 is turning off, pump 2 will turn off as well. And if after a second pump turns on, pump 2 and 10 seconds and not enough pressure, this is 5 seconds, this is 10 seconds, we're going to do a B coil. Okay, if that B coil turns on, what are we going to do? B turns on. And we seal it. And again, pump 1 is our disconnect, and pump 3 is now turning on. So we now have a circuit that does something entirely different. But what's the difference? We've added seal circuits here, haven't we? We've added a seal circuit here, we've added a seal circuit here. Which is better? Don't know. You decide. And you may end up having to do that in your life to decide which is a better circuit, but that's something that you may or may not do. Okay. Number 23 we're going to skip. Number 24. This one is a little bit more interesting. How do you want to say interesting? It's a little different. 24 is a question that okay, so number 24 and number 26, 24 and 28 are basically the same. I want to work 28. I guess I would rather work 24. I'm sorry, I'm going to go back to what I originally did, 24. So this one is a problem that basically says you're going to do something, and then you're going to do something else, you're going to do something else, you're going to do something else. So basically, you push the start button, and you seal it. Okay. So, start button, PB1. And it says you keep running until something happens. We don't know what that is yet, but we're going to just say okay. And you're going to run, and this is basically run to the right. This call this A. And in the middle, when you're running down that way, A and you see the photo eye, middle photo eye. Let's call it the middle photo eye. You're going to say, I'm going to seal that circuit, and I'm going to turn it off. And I don't know exactly what's going to take to do that, but this is going to be B when I'm spraying. So this is going to be the whole cycle. This will be while I'm spraying. When I get to the right photo eye, and I'm at B, I'm going to seal another circuit, call it C. And this says turn around and go to the left. So now we've got all these circuits here, and we don't know how to turn them off or whatever, but I think now you can start to see the pattern here. The C and the left photo eye gives me a bit called D. D turns this whole puppy off. Now when do I spray? How do I make my machine go to the right? Well, it's what? To the right is A, but not C. Spraying is B, but not C. So B, but not C, is I am spraying. Going to the left is C. And I've got an answer. It may not be a perfect answer, but it gives me a little bit of an idea how that kind of a position works. So basically they feed the next one, they feed the next one, they feed the next one, they feed the next one. Okay, think about it a little while. Hopefully that helps. Okay, number 25. 25, don't do this way. In other words, you would have probably answered, I want to do this one, but not the other, but not the other, but not the other, okay? And that seals the one. Then I seal the next, right? I seal the next. This one, but not that one, but not, you follow me? It's the, I have 4 circuits that all, this would be bin 1, but not bin 2, but not bin 3, but not bin 4, bin 2, but not bin 1, but not bin 2, but not bin 3, but not bin 4. I have 4 of these. What's wrong with this? What if you have a real hungry bin and it is number 1? And this is where your logic starts. Bin 1 always is serviced. Bin 2, bin 3, bin 4 are not serviced. You want the first one dry to get serviced, right? So you need a stack. That implies something from chapter 12, which we're going to talk to. So you can design it this way, but it has a fault. And the fault is you can starve a certain furnace or certain bin if you design it this way. You need a first come, first serve, like in a grocery store. Get in a line. If you don't have a line, there's no preferential treatment here. So this is a thinking problem, and it's also, you can design it. You can design this, but it's not the right way to go. The stack and the FIFO, first in, first out, is the way to go. So that's my answer to number 25. You can do it, but don't do it. Number 27, we already solved one like it. Number 28, we're going to solve this again, and it says 5 times. Don't worry about the 5 times. So that gives you some answers to some of the questions at the end of chapter 6. Lots and lots and lots of fun, right? Okay, take care. Have a good day.